Hello and welcome. In this video, I just walk you through the complete example of UVM. So for this example, we are considering a combinational adder. Okay, as you can see here, it has two input, one output. An output is equal to sum of these inputs A and B. As you can see, this is a piece of RTL code which is written in System Verilog HDL. You can use any HDL, VHDL, Verilog or System Verilog. So module RTL, adder RTL and module. Inside this input, I'm declaring logic and output also logic. Input A and B of size 4 bits and output is of 5 bits, so that we can consider a carry here. And this is a procedural block always underscore com. Y is equal to A plus B. Output is equal to sum of input. Very simple. So as a verification engineer, we have the black box visibility of the DUT. So as you can see here, just this RTL will have a black box kind of thing. Input and output, inputs and output ports we have only. We don't know the internal architecture of the design. So if you synthesize this piece of hardware, you'll find the synthesized result something like this. So this A and B, and this is Y output, and Y is equal to sum of this A and B. Now we are considering this black box for our verification, because as a verification engineer we have only black box visibility. This is what a simple test bench architecture we are considering. It is always good practice to use this test bench architecture, to draw the test bench architecture before moving towards a code. Okay, so as you can see over here, the top TB, HVL top TB, in which we are declaring the instance of test, we are calling a run test over there. This test class, in which we are creating this environment and the sequence also, and in the test we are starting this sequence onto this sequencer which is there in the agent of this environment. So this environment is a component class. This test is also a component class. So this environment has agent component, and we are considering an active agent. So it will have all the three essential components like sequencer, driver, and monitor. So the sequencer is just a mediator between the sequence and driver, and it is connected to the driver using TLM transaction level modeling, port and export. Now the driver is the driver responsibility is to drive this stimulus to the DUT with the help of this interface. And on the other hand, this monitor is there, which is responsible for capturing this data from DUT through this interface and broadcast this data to multiple components like a scoreboard, coverage collector, or other components. But here in this particular example, we are considering a scoreboard. This scoreboard is used to do a comparison with our golden data. Okay, so monitor has analysis port, or you can say the broadcast port. So it will broadcast this data to multiple components, and a scoreboard is there which has this analysis implementation port. Okay. So this is what the complete test bench architecture for verifying a combinational adder, or it is a generalized test bench architecture of UV. Now let me show you the code over here, complete test bench architecture as well as hardware code. So this is what the RTL code already we discussed. then this is what a simple interface. We are not considering a clocking block and mod ports over here. So in the next example, which will be the sequential adder, we will consider this mod port and clocking blocks over there. So this is a simple interface, a interface and interface, in which we have to declare all the inputs and outputs as a logic type, same size as we declared in the RTL. Now let me show you the complete test bench architecture. Now here these two lines are mandatory. First line will include all the UVM macros. Second line will give us an access to all UVM classes. Now first we have to write a transaction class. Okay, so this is a class sequence item, extends from UVM sequence item, and here we are declaring the inputs, logic and rand type. So in future, if we are using the pseudo random number generation facility, we can randomize them. And we are just declaring output as a logic because we are not randomizing. And this is a field registration macros, factory registration and field registration macros. Take UVM object details begin and end. And inside this take UVM field int for A, B and Y output. And these are some flex UVM default. So it will, or you can use UVM all on also. So that we can make use of all the inbuilt methods such as print, copy, compare and all. And plus UVM decimal flag is to print the properties in decimal format. As it is an object class in the UVM base class hierarchy, its default constructor only expecting one argument, end class sequence item. Now the next class is sequence, as you can see. So sequence one we are giving, which is extending from UVM sequence, and as it is a parameterized class, we have to parameterize with the type of transaction this sequence item. Remember in UVM, sequence, sequencer and driver, these three classes are the parameterized one. Then as it is also an object class in the UVM base class hierarchy, we have to register with tick UVM object details and its default constructor expecting only one argument. Now as you know that in UVM, object class does not contain any face, so the executable logic we need to write in the body method. Okay, so inside the virtual task body, we are creating the object for REQ. This REQ is an inbuilt object of the transaction class, and we are using repeat 5. So 5 times it will repeat this particular activity. Within begin end block, we are using start item and finish item tasks, and inside that we are randomizing the inputs A and B, and just we are printing a method data same to driver, and just we are using the print inbuilt method to print this entire things A, B and Y, and end class sequence one. Now the next class is sequencer. Okay. So as it is just a mediator between sequence and this driver, just we have to write class sequencer, which is extending from UVM sequencer, parameterized with the type of transaction, and just factory registration macro and default constructor. As it is a component class in the UVM based class hierarchy, we have to use take UVM component details factory registration macro and its default constructor expecting two arguments. Okay. Now another class, as you can see here, the driver class. Okay. We have to define class driver, which is extending from UVM driver. As it is also a parameterized class, we have to parameterize with the type of transaction. Okay. Then as it is a component class, we have to use take UVM component details and default constructor with two arguments. Now in the build phase of this driver, we have to create the object for this REQ, which is an inbuilt object of our transaction class, and we are getting the virtual interface. Okay, let me show you the top class first so that you will have the clear understanding of that. So this is what a top TB. Okay, inside this we have just declaring the interface, adder interface, and VIF instance we are giving, and this empty parenthesis is mandatory. Then here we are instantiating our DUT. Okay. And within initial begin block, we are using UVM config DB facility for setting this virtual interface. Okay, so virtual adder interface ::set, and it expecting 4 arguments. Remember, set and get expecting 4 arguments. So first argument is null, and this in star we are giving in double quote, so that this particular instance interface will be visible for all the components in the UVM base class are here. And this is what a key we are giving, virtual INTA, and this is what variable VIF. For this VIF we are setting. Okay, and within initial begin with just calling run test the run to run the test. Okay, now let me show you the driver code, so that now you will have the clear understanding how we are getting that in all the components. So as you can see in the build phase of this driver, we are getting that virtual interface. Okay, so if not of UVM config DB virtual interface, and the syntax for getting is also same: : get, and this within parentheses we have to provide 4 arguments. First 2 are this and empty double quote, then the same string which we have set it, and the variable VIF. Okay, if it is not, we are not getting, then we have using UVM fatal, and which is showing the message that unable to get interface, and just end function build phase. Now the another important phase is run phase in the driver. Here we are driving this stimulus to the DUT. Okay, so within forever begin block, we have to use sequence item port dot get next item, and sequence item port dot item done. Inside that we have to drive this A and B inputs to the DUT through this virtual interface. So this VIF dot A, we are using non-blocking assignments for driving. So this REQ has that data, randomized data dot A. So with this we are driving A and B inputs to the DUT with the help of this VIF virtual interface, and just we are printing that data sent to drive DUT, and printing using print method whatever data which we are sending to the DUT, and just we are giving a random delay #10 over here. Then end task, run phase, and end class driver. Now the next component is monitor class. Okay, so class monitor, which is extending from UVM monitor, and it is not a parameterized class one. Okay, so sequence item, we have to declare the object for this transaction class, sequence item trans we are giving, and we are getting this, we are declaring the interface as a virtual. As you know that in the test class we have to declare this interface as a virtual, because the interface is an static component, and whereas the classes are the dynamic in nature. So to access that static component in this dynamic verification environment, we have to make them as a virtual. Okay. Now as monitor has this analysis port, we have to declare that UVM analysis port, and it is a parameterized one, so we have to parameterize the type of transaction sequence item, and name is AP we are giving. Now as it is also a component in the UVM based class hierarchy, we have to use stick UVM component details along with its default constructor, which is expecting 2 arguments, and this we are allocating a memory for this analysis port new constructor. Now in the build phase, we are creating the object for this transaction class. Okay, and here also we are getting that virtual interface. If we are not able to get, then we are using tick UVM fatal and printing a message that unable to get virtual interface. Now in the run phase, here in the monitor, for within forever begin block, we have to give the same delay whatever we gave in the driver class, and we have to capture the inputs and outputs stream. So the monitor is capturing the data from DUT with this interface. So as you can see, VIF.A we are capturing in this transaction object. Okay. Transaction.A. This is the right hand side has this information of this DUT, through this virtual interface we are capturing in the monitor. Okay, so trans dot a, b and y we are capturing, and just we are printing a message data sent to scoreboard, and we are using the print method to print the a, b and y. And this analysis port, the data collected data we are putting this analysis port inside this analysis port. So ap dot write is a method we'll see in the scoreboard, and this transaction it has the captured data, so we are putting that captured data into this analysis write method, analysis port write method. End task run phase and end class monitor. Now another class is agent config class. So in this agent config class, just we are making the active or passive agent. So the parameter for that is tick uvm active passive enum is active is equal to uvm active. So with this config class we can make agent as active or passive. So active means it will have all the three essential components like driver, sequencer and monitor. If it is a passive, then it will have only monitor. Okay. Then it is an object class. So take UVM object details and its default constructor expecting one argument. Now the agent class, this is a agent class in which we are declaring the instance of all these three essential components, driver, sequencer and monitor. And we are creating in the build phase, and in the connect phase we are making this connection. Okay, so this sequencer has sequence item export and driver which has the port. Okay, so this driver is an initiator, so we'll have to make a connection with this driver port with this sequencer export. Okay, now in the agent we are declaring the instances for agent config, driver, sequencer and monitor. As it is a component class, we have to register with a tick UVM component details and its default constructor expecting two arguments. Now in the build phase of this agent, we are creating this monitor and agent config, and we are checking that if UVM config db agent config get agent configuration. Okay, if we are not able to get that configuration agent, which is we are setting in the top level class like test class, let me show you that once. So inside a base test you can see we are creating the instance of environment and this agent config, and in the build phase we are setting this agent config, first creating that using factories create method, and here we are setting that uvm config db agent config db. Okay, set this empty this, and inside this we are setting this agent config for all the components. So all the components star we are giving, so all the components can get this whatever we are setting, and the string the key is agent configuration, and for this acfg variable we are setting. And here we are in the top level class like base test we are setting, and in all lower level classes we are getting. So inside the agent class, as you can see here, we are getting that. Okay, so if we are not able to get that agent configuration, then it will give the fatal error. Okay. If ECFG whatever we are getting dot is active equal to UVM active, if it is an active agent, then only we'll create driver and sequencer. Remember, active agent has driver, sequencer and monitor. If it is a passive agent, it will have only monitor. So anyhow monitor is there, we have to create that. Okay, if that is active is equal to UVM active, then only we'll create driver and sequencer. Now in the connect phase, this is an important phase. Here we are making connection of this driver and sequencer. Okay. So inside this connect phase, we are getting this is active equal to UVM active. Then we are making a connection with this driver. So driver has a port and which is an initiator. So we have to make a connection with initiator. So driver dot sequence item port dot connect to the sequence item export. So as you can see, driver has this port. We are making drivers dot sequence item port dot connect to the sequence item export. Okay, so with this that connection will be there. End phase, end function, connect phase, okay, and end class agent. Now the next important class is an scoreboard. So as you can see, scoreboard has this analysis implementation port. So we have to define scoreboard, which is extending from UVM scoreboard, and here we have to make use of this transaction class. Okay, data, we are declaring the instance as data here, and it has analysis implementation port, so tick UVM analysis port and parameterize with type of transaction, and as it is expecting two arguments, we have to provide two arguments. First one is type of transaction, then the implementation detail where we are defining the implementation detail. So here inside a scoreboard only we are defining, so the second argument will be scoreboard class only, and the name for this analysis port is AIP we are giving. And as it is a component class, we have to register with tick UVM component details, and its default constructor expecting two arguments, and we are creating this AIP, allocating a memory for this using new construct. Now inside a build phase, we have to create the object for this data, okay, which we have declared with the type of transaction class using factory script method. And inside this, we have to define this implementation detail. So which is, as I told you, it is a function which is not returning anything, just a virtual function void write. Okay, inside that we are declaring the sequence item instance t. Okay, and we are just printing the data received from monitor, and with the help of this print method we are printing to see whether whatever the data we are receiving in this code, and we are writing a comparison logic. What we are writing, if the output equal to addition of this input a plus b, then we are saying test is pass. Else we are saying if it is not equal to, output is not equal to addition of inputs, then we are saying test is fail, and just end function write. Okay, and end class is scoreboard. Simple, very simple. So this scoreboard has analysis implementation port, and this write method implementation details we are writing here. Okay, now the next class is environment, as you can see. So inside this environment, we have to create the instance for, we have to create this agent and scoreboard. So here also you can see we are declaring the instances for, first we are declaring class environment, which is extending from UVM environment, declaring the instances for scoreboard and agent. And as it is now also a component class, we have to register with tick UVM component details factory registration macro, and this its default constructor expecting two arguments. Now in the build phase, we have to create the objects for this scoreboard and agent using factory create method, and in the connect phase we have to make a connection of this analysis port of this monitor with this analysis export of this scoreboard using TLM. So as you can see in the connect phase, as monitor is an initiator, we have to start the connection from there. So monitor dot analysis port dot connect to the scoreboard analysis implementation. So as you can see, monitor, which is there in the agent. Okay, so agent dot monitor dot analysis port dot connect to the scoreboard analysis implementation. So as you can see, agent dot monitor dot analysis port dot connect to the scoreboard analysis implementation. This is what a connection in the environment we are making between analysis implementation port of scoreboard and analysis port of monitor, which is there in the agent. Now the base test class, now next top level class. Here we are creating the instance for environment, which is extending from UVM test, and this base test, which is extending from UVM test. So here we are creating the environment, and the agent config we are setting that. Okay, so as it is also a component class in the UVM base class hierarchy, we have to register with tick UVM component details and its default constructor expecting two arguments. Now in the build phase, we are creating this object for this environment and agent config, and here we are setting that config, agent config here, right? As we discussed before. Now in the end of elaboration phase, just we are printing the topology in order to see the test bench architecture, complete test bench architecture. Now in the report phase, what we are saying, so this report phase is used to display the simulation result, whether the test is pass or not. So inside this report phase, which is UV which is also a function. We are declaring the instance svr, which is of uvm report server, and we are creating svr, and we are saying svr is equal to uvm report server and get server we are using here. Inside that we are saying test fail or pass. So what is the parameter for fail or pass is if this svr dot get severity count uvm fatal plus get severity count uvm error. If both are greater than 0, then we are saying test is fail, else test is pass. So for example, if we are getting any error like uvm fatal or uvm error, then the test will fail, else the test will pass. And this is end function report phase and end class base test. Now the important class is test class. Inside that we are this test one, which is extending from base test with this base test, and inside this we are declaring this sequence, okay, and instance, and as it is an object class, sorry, a component class, we have to register with component details and default constructor expecting 2 arguments. Then in just we are calling this build phase. Okay, so this build phase will do all the things like that. That build phase contain a logic of creating this of defining this UVM, of defining this agent config, and it will create the environment. Okay, so no need to do those things again and again. Just we need to call the parents build phase. So this is a parent. This will call to the parent class, meaning this base test class, which will set the agent configuration and create the environment. Now here in the run phase of that, we have to create the instance. We have to allocate a memory for this seq sequence 1 instance using factories create method. And inside this run phase only, we have to raise an objection and drop an objection. And inside this, we have to start this particular sequence onto this sequencer, which is there in the agent of environment. So as you can see, we are starting this sequence onto this sequencer, which is there in agent of this environment. We have to provide this complete hierarchical path here. Okay, and as you know that this start method will call to the body method of sequence, and body method of sequence and run phase of driver both will execute in parallel. Okay, and inside this stop module already we discussed, we are declaring the virtual interface VIF instance for this interface, and then we are instantiating our dot, and inside this initial begin we are just setting the virtual adder interface using config db, and then just we are calling a run test. So this run test is a method which is task which initiate to execute all the phases starting from build phase to the final phase. And just in another initial begin block, we are calling this dump file and dump pairs in order to see the waveform. Now we will run this code and we will try to analyze the output, whether we are getting the result as expected or not. So let me run this code once. So after running this, we will analyze the output. So inside the sequence, as you remember, we used repeat 5. Okay. So it will generate 5 random transactions. So we'll try to observe that. So first it will print a topology in the test. Okay. Test 1. We are printing a topology. Okay. Sorry, inside base test we are printing a topology. So as you can see here, we have test 1, which has, then we have environment, we have agent, driver, and we have monitor. So this driver has analysis port, okay, remember, and monitor this, it has analysis, driver has this port, and as you remember here, driver has this port, and then this monitor has analysis port, broadcast port you can say, and this sequencer which has analysis export. Then we have a scoreboard which has analysis implementation port. So this is what the complete topology, what our test bench architecture consists of. With this we can understand what the components we have created here in the test bench architecture. Now this is a sequence one which is generating some random data. So as you can see, A is 14, B is 0. So we are sending this to driver. At this driver we will find this A is 14, B is 0. And in the monitor we are capturing the information, right? A, B and Y. So A is 14, B is 0. So output will be 14 only. And this is a scoreboard class, data received from monitor analysis port. So in this scoreboard, as you can see, 14 and 0, addition of this A and B is equal to 14. So the test is passing. We are getting the result as expected. Now the second time it will generate 4 and 6, so which will be 10. Driver will also get 4 and 6. Now in the monitor we are capturing the input and output both, so 4 and 6 is equal to 10. In the scoreboard we are getting the same 4, 6 equal to 10. We are printing that. So as you can see, test is passed and is scored. Now the third time it is 8 and 14. So as you can see in the driver also 8 and 14, and in the monitor we are capturing A, B and Y. So 8 and 14 is 22. So scoreboard same 42, 22. Then at the scoreboard you can find the test is passed. Similarly for all the type or the transactions, like for the 10 and 10 should be 20. Okay, so driver is getting 10 and 10. Then at the monitor 10 and 10, 20. At the scoreboard also 20. Then test is passing. So this is what the complete example, and as there is no any UVM error and no fatal, hence we are getting the test pass from the report phase of that test. Okay, so with this I hope you have understood the complete architecture of UVM for a combinational adder, and also I hope you have enjoyed this video. So thanks for watching. Thank you. In the next video, we will try to understand the sequential adder, and in that we will try to make use of mod ports and clocking blocks in the interface, and also we'll try to take the help of we'll try to add the concept of virtual sequence and virtual sequencer, so that you will have the clear understanding of the concept of virtual sequence and virtual sequence. Before that, I will request you first go through the video which already I have posted on my channel, that which explain the concept of virtual sequence and virtual sequencer. So if you have the theory knowledge, you can easily understand the next video. So again, thank you for watching this video.